Hi. Let's move on through bonding into talking about something a little bit different. Usual idea. Although this image kind of gets the point across. We're gonna watch the video and record any interesting observations or questions that you have. I mean, water should go down, and it's not. It's being pulled to the side. Some sort of force is working on it. That force might be due to something in the water or in the balloon, but I'm going to guess it actually has to do with both. So we know that the balloon got rubbed with the cloth, and I've seen that before. You know, you rub it on your hair, you rub it on the cloth, and the balloon will even stick to the wall. But to understand that, I think I want to talk a little bit about water as a whole. We've got one electron for each water, plus six is a total of 8 electrons. I think most of us have drawn this before, but I'll go through the process really quick. Don't forget, oxygen has two pairs, two unpaired electrons. So there's a bond made between the unpaired electrons of hydrogen and the unpaired electrons of oxygen in each case. So the structure we get here is this. And this is an important structure. That's why I'm taking the time to draw it now. This is going to be a cornerstone of probably the next few lessons, talking about what water is and how it works and why it does what it does. But we're going to use this structure going forward to understand what was happening with the balloon. So to just come out with it, there is such a thing as unequal sharing between two atoms when it comes to these electrons. And since these electrons exist in a cloud in a molecular orbital in between the two nuclei, if the sharing is unequal, then the cloud is unequally spread, and then that means that the electrons are have a little bit higher probability being closer to one atom over the other. And so here's our water again, and this would be for contrast a molecule of hydrogen down here, and this one would be a molecule of HF over here. Now I understand that some of the cloud that you're seeing here is probably due to the lone pairs of fluorine, but you can even see in the space between the hydrogen and the fluorine, there is a higher density of the cloud towards the fluorine. What this causes is something that we're going to call polarity of the bond. There's a separate lesson where polarity of the bond. There's a separate lesson, the next lesson where we're going to, or maybe two from now, where we're going to talk about the molecule as a whole, but right now we are focusing on the bond. A nonpolar bond, otherwise known as pure, this is equal sharing. This one down here is nonpolar. Whenever you have two different atoms, there is some degree of polarity to the bond. So in terms of the bond, this is nonpolar bond down here, and this is a polar bond on, these are both polar. This is polar, and this is polar. All three, we can talk about them all separately. Like I said, when that cloud is lopsided, it causes a partial charge. So this symbol that you're seeing repeated everywhere here is a Greek lowercase delta. And so the idea is that if the electrons are spending more time towards the fluorine, then the fluorine side of this bond will have a slight negative charge, in that if you picture that tug of war that we've seen several times before, it's almost like the fluorine is starting to win and the rope is more piled up over there. It's just that in this case the rope is negatively charged. Where the electrons aren't, or are there less frequently, there's actually a slight buildup of positive charge. In both of these cases, this slight positive is always less than a full ionic charge. The degree to how slight and how negative is not really super important. We're not going to try and put a number to it. That said, we're going to talk about different ways of finding whether or not that bond is more or less polar. So to establish our discussion here, we've got three different situations where atoms are bonded to hydrogen. We've got here a bond where hydrogen's bonded to hydrogen, here where oxygen is bonded to hydrogen. And if we were to draw out a Lewis structure for a molecule of methane, it would look like this. If you need to pause and go through that yourself to see where it came from, go ahead. Total of 8 valence electrons, single bonds to all the hydrogens. So here's our carbon-hydrogen bond. Is there a way that we can say, even without knowing, right? We do know that they're all partially charged, or in the case of the hydrogen-hydrogen bond, not charged at all. Is there a way to say, is that partial charge larger or smaller without putting a number to it? And the answer is yes. Because if you go back to our old definitions, the definition of electronegativity was attraction for electrons in a bond. Well, now we actually know what those bonds are and how they work. So yes, we can have that discussion. This means that you need your reference tables, unless you're going to spend a really long time pulling up numbers that may or may not match what you're familiar with and what I expect to see. Go to table S and just use the numbers that are there. So I have a copy of the green book here, and I'm going to go to the page about table S, and I'm just going to write down the numbers, see what we can make of this. So the electronegativity for hydrogen is 2.2. The electronegativity for carbon is 2.6, and the electronegativity for oxygen is 3.4. If this number is a score of how much pull the atom has on electrons, these are all not really useful in a vacuum by themselves. We should be having instead a discussion of the relative imbalance, the relative asymmetry of the pull. So instead of talking about the electronegativities, we're now going to spend a large amount of time talking about the electronegativity difference. In a hydrogen-hydrogen bond, the difference is 0. So in this case, if we have a 0 difference, that's where we get our nonpolar bond. The difference between carbon and hydrogen is 0.4, and the difference between hydrogen and oxygen is... Okay. Now we can have a bit of a discussion. We can rank these. So this difference in electronegativity means the pull on the shared electrons between oxygen and hydrogen by oxygen is stronger than the pull on the electrons shared between carbon and hydrogen by the carbon. So if we were to represent it this way, and you probably shouldn't beyond this slide, if we were to represent it this way by making the symbol bigger, this would be a bigger negative, and this would be a much smaller negative, and this would be a smaller positive, and this would be a much bigger positive. Still not big enough to be an ionic plus and a minus, but it's more polar and less polar, and then nonpolar. No partial charges written here. That said, this does actually bring to light something I have wanted to mention for a while. The idea that there's two different kinds of bonding is a bit of an illusion, because if the bond got more and more and more and more polar, what you might imagine is that eventually there's some point where the discrepancy of pull will just have the electrons completely housed on one of the atoms and not the other. And that's really an ionic bond. Now, some people, and you can, of course, you can look up the values and you can compare the electronegativity differences of metals and nonmetals, but you know that metals having a low electronegativity and nonmetals having a relatively high electronegativity, the difference is going to be really large. And so what this kind of sets up is a continuum where the difference goes from 0 to, probably about 3.1 or so, or 3.2 or 3.4, because the lowest metals are at like 0.8, 0.7, maybe 0.6. But in the middle is where the polar bonding, the polar covalent bonding exists. To that point, there's also this term called ionic character, which we relate completely back to an electronegativity difference. There is a point where the bonding just becomes ionic, but even within that, how ionic is actually a question we can ask. In this way, everything said here is fine. It's really hard for me to put a number where things cross over from being polar covalent to being ionic. Some textbooks say that the number where it crosses over is about 1.6 on the difference scale. Some people say it's about 2. The reason why it's a range is because you kind of have to look at the compounds in general. I mean, going back to what we said before, the difference of 1.2 and 0.4, those are polar covalent bonds. We're well below that threshold. But there are a couple examples, like in the case of HF, where the difference is quite large. It's at 1.8 on the electronegativity scale. So if we said that the hard line was 1.6, HF would be an ionic bond, and, well, I mean, I just showed you it wasn't. It's a covalent bond, 2 nonmetals. There are some examples where certain metals and nonmetals will actually end up doing something pretty strange too. Sulfur has an electronegativity value of 2.6, and copper has an electronegativity value of 1.9. So we're getting a difference of 0.7 here, which is then really low. So it's hard to say definitively that there is a line where the bonding stops becoming polar and starts becoming covalent, which is why I usually rest on saying, are there metals and nonmetals, and I go from there. And instead, I have a discussion of more polar and less polar. So for a couple of examples, if you want to draw these molecules, you can hit the pause button and do that yourself, but I'm going to quickly put in the structures so that I can have this discussion. Don't forget that sodium fluoride is, of course, ionic. So the questions here, which of the following are least polar? Which pairing has the most ionic character? The best way we're going to have this discussion is to figure out the electronegativity difference of each. We already established the difference between a CH is a 0.4. It was 1.2, I believe, for the OH. This is our CH of 0.4. It actually does not matter where in which molecule these exist. A CH bond, in terms of this electronegativity difference, is a CH bond. A CO bond is a CO bond. A CC bond is a CC bond. So the difference here is, in fact, 0. And then, like I said, oxygen is 3.4. Carbon is 2.6. So that's, wow, that's a big difference. Carbon is a 2.6. That's like 1.8? 0.8. 0.8, right? I can do math. 34 minus 26, yes, 0.8. So here our CO electronegativity difference is also a 0.8. It doesn't matter if it's double bond or single bond or triple bond. You know, a carbon-oxygen bond is a carbon-oxygen bond in terms of polarity. So we can go through this whole process. NAF, let me do that really quickly, 0.9. So 4.0 minus 0.9 is a 3.1. So the most ionic character... Most ionic character is NAF, and the least polar would be the CC bond, and I'm sure you could establish a ranking from within there. So to round things off, polar bonding is a thing, nonpolar bonding as well, so we've subdivided our covalent bonding model into equal and unequal sharing. The actual line for where polar becomes ionic is kind of variable. It's also somewhat kind of variable depending on which books you read, where polarity becomes non-polarity. Some people say it's less than 0.4. Some people say it's 0 or it's polar. Personally, I subscribe to the second one of those. The more electronegative atom is always the one with the slight negative charge. The larger the difference, this becomes a higher ionic character. So you can still have a covalent bond with a higher ionic character than a different covalent bond. And the last thing I'll mention is that it's possible to look at a whole molecule, and don't forget, and say that is a polar bond, and divorce that from the rest of the molecule, saying I'm going to consider each bond separately. Of course, you could add them all together, but I'm going to save that for later. Thanks for watching.